Swayam Prabha. Digital India. Educated India.
So, last class I have discussed about the bearing capacity determination, then if the soil has the local shear failure, intermediate case. Now, today I will discuss that this effect can be incorporated in another way by considering the effect of soil compressibility. Okay. So, that means as I discussed that the local shear failure can be incorporated by compressibility effect also in the soil, because this is due to the compressibility of the soil. So, that means this is our general bearing capacity equation, that means the shape factor, depth factor, inclination factor is given. In addition to, there is another factor is introduced, that is called compressibility factor. Okay. So, this is Cc, Cq and C gamma. So, now how I will calculate these value. So, this is basic suggested this compressibility effect of the soil in 1973. So, where another factor is incorporated. So, we know generally basically we have three factors, that is the shape factor, depth factor, inclination factor. So, another factor is introduced, which is called the compressibility factor, which is the Cc. And later on I will introduce two more factors. One is the tilt base factor, another is the sloping down factor. So, basically it is not three factors, basically it is 6 factors total we can incorporate in a bearing capacity equation. So, in our normal foundation engineering course we generally deal with these 3 factors, but actually we can incorporate 3 more factors. One is compressibility factor, another is the tilting base factor, another is the sloping ground factor. So, those things I will discuss later on, but now I will discuss about the compressibility effect. So, what is the steps? So, steps is that I will discuss the steps. So, first I have to calculate the rigidity index. So, step 1, so step 1 that we have to calculate the index IR, okay, at a depth of B by 2, where B is the width of the footing from the base of the foundation. So, we have to calculate the rigidity index IR at a depth of B by 2 from the base of the foundation. So, how we will calculate the rigidity index IR? So, that IR can be calculated by G into C plus Q dash into tan phi. Okay. So, where G is the shear modulus and Q dash is effective overburden pressure. Pressure at a depth of df plus b by 2. So, that means suppose we have a footing whose width is b and this is the depth of the foundation. So, we have to calculate this rigidity index at a depth of df plus b by 2. Okay. So, at the depth of df plus b by 2. The next step is calculate critical rigidity index. Okay. So, calculate critical rigidity index, which is CR critical is equal to half, then bracket exponential of 3.30 minus 0.45 b by L cot 45 degree minus phi by 2. Now, in this case, that if b by L is equal to 0, that means length is much larger than the b, then it is called the strip footing. This is true for all the cases actually. Strip footing, and if b by L is equal to 1, then it is called square footing. Okay. So, now this is the case. Now, if b by L equal to 0, that means this part will be 0, only 3.3 cot 45 degree minus phi by 2 will be the within the exponential part. Now, if now the next condition, that if IR, that means the rigidity index is greater than equal to IR critical. So, that means that this is a critical value if the rigidity index, that means soil rigidity index is more than the critical rigidity index, that means the soil is very steep. So, that means no compressibility effect or corrections are not required. So, that means the similar to the general shear failure. So, that means if IR is greater than equal to IR critical, if it is the rigidity index is more than the critical value, that means it is similar to a general shear failure. Okay. Where this correction will be definitely 1, because its soil is very rigid. So, that means it is a general shear failure type. So, all the corrections will be 1. So, that means in such case the CC, CQ and C gamma all will be 0, will be 1. So, that means it is similar to the general shear failure case. But if it is not, now if your IR is less than IR critical, then we have to apply the corrections, because now that may be the local shear failure or in between that. So, we have to apply the corrections factor. So, that correction factor we can calculate that CQ is equal to C gamma, that will be equal to exponential minus 4.4 plus 0.6 b by L tan phi plus 3.07 sin phi log 2 IR divided by 1 plus sin phi okay, this is the equation to calculate CQ and C gamma. Now, for phi is equal to 0, then CC is equal to 0.32 plus 0.12 B by L plus 0.60 log IR if phi equal to 0. For phi greater than 0 degree, then CC is equal to CQ, we have to calculate CQ minus 1 minus CQ divided by NQ into tan phi. So, these are the corrections factor we have to apply to incorporate the compressibility of the soil. Now, I will solve one example problem and then we will see how we can incorporate that effect into the bearing capacity. So, that example problem is given the same similar rectangular footing of size 3 meter cross 6 meter is placed at a depth of 1 meter in a homogeneous E5 soil. The water table is at a great depth. The unit weight of the soil is 18 kilonewton meter per meter cube. Determine the net ultimate bearing capacity when C is equal to 50 kPa, phi equal to 20 degree. Modulus of elasticity of the soil is 6 MPa and Poisson ratio is 0.35. Use basics equation. The load is vertical and acting at the center of the foundation. So, that means no eccentricity, no inclined load, it is acting at the center of the foundation, it is vertical also. So, we have to use the basic bearing capacity equation. So, first as the modulus of elasticity is given, so we can incorporate the compressibility effect, because in previous case in Tazaka theory, the example that I have solved, where based on the phi value we have to judge whether we have to apply the local shear failure or the general shear failure. But here if we have the modulus of elasticity or shear modulus or Poisson ratio, these values, then automatically we can understand whether this compressibility correction you have to apply or not by calculating the rigidity critical rigidity index and rigidity index. So, let us see whether in this case the compressibility soil compressibility correction is required or not. Okay, so, this is the equation that I have discussed. So, first I have to calculate the IR, which is the rigidity index. So, that value is given G plus C plus divided by C plus Q dash tan phi. Okay. So, now here E is given. So, from the E I can get the shear modulus. So, that is E is G is equal to E divided 1 plus mu. So, E is given 6 MPa, that means 6 into 10 to the power 3 kPa divided by 2, 1 plus mu is given 0.35. So, G value is coming out to be 2222.22 kilonewton per meter square. Okay, so, G value is this one. So, I can put that G value divided by C is 50 kPa plus, as the effective overburden pressure, because here we have to calculate the effective overburden pressure where at a depth of df plus b by 2. Okay. So, that df is 1 meter, depth of foundation is given 1 meter, b is 3 meter. So, 3 divided by 2. So, 1 plus 1.5, so 2.5. So, we have to calculate that q dash at a depth of 2.5 meter from the ground. As the water table is not present, so remember that it is effective overburden pressure. As in this case water table is not present, so that is why directly I can calculate with total pressure, because here total pressure, effective pressure both are same. But if water table is present, then you have to calculate the effective overburden pressure, remember that. So, that means here q dash will be 2.5 into unit weight is 18, 2.5 into 18, which is 45 kilonewton per meter square. So, that is why 45 into 10, 20 degree. Okay. So, that means here this value is coming out to be 33.48. Now, I will calculate the IR critical, which is half, then EXP 3.3 minus 0.45 B by L into cot 45 degree minus 5 by 2. Okay. So, I will put this value half (3.3) minus 0.45, B is 3 meter, L is 6 meter, then cot 45 degree minus 20 degree divided by 2. So, this is coming out to be 40.38. So, you can see that the critical rigidity index is 40.4 around, and the rigidity index is 34. So, which is very close to the critical rigidity index, but it is less than critical rigidity index. So, we have to apply the corrections. These values are, correction factors are not 1. Okay, but by looking at these values, you can understand that these values will be close to 1, because the difference between IR and IR critical are very small. So, that is why the rigidity of the soil is very close to the critical value. So, that is why it will be, because if the IR is equal to IR critical, then the correction factors will be 1. So, as these values are very close to each other, so it is expected the critical, the correction factors will be very close to 1. Okay. Because if the difference is more, then that value will be very less, this value will be less, but here, or less than 1. But here it will be less than 1, but very close to 1. Let us see. So, now the as these values I can see that my IR is less than IR critical. So, I have to calculate these factors. So, these factors CQ, C gamma is equal to exponential minus 4.4 plus 0.6 B by L tan phi plus 3.07 sin phi into log 2 IR divided by 1 point sin phi. Okay. So, I can write that is exp minus 4.4 plus 0.6, B is 3, L is 6, tan 20 degree plus 3.07 sin 20 degree into log 2 into 33.48 divided by 1 plus sin 20 degree. Okay. So, this is the values. So, finally, it is coming out to be 0.94. As I mentioned, the value will be close to 1. So, it is coming 0.94. So, similar to I can calculate the other factors, that is Cc. So, that is Cq minus 1 by Cq Nq tan phi. Now, it is basic equation you have to consider. Now, for phi equal to 20 degree, my Nc is equal to 14.8, Nq is equal to 6.4 and N gamma is equal to 5.4. Okay, because here we have to consider the general shear values directly from that table, because the compressibility effect itself will take care the local shear failure or intermediate failure. So, that correction will itself take care that. So, that means here this is the value. So, now Cq is 0.94 minus 1 minus 0.94, Nq is 6.4, it is tan 20 degree. So, this value is also very close to 1, which is 0.914. So, now we have calculated the compressibility factors. Now, we have to calculate the shape factor, depth factors or inclination factors will be 1 all the cases. So, I will calculate, because as per basic. So, Sc is 1 plus Nq by Nc divided into B by L, which is 1 plus 6.4 divided by 14.8, B is 3, L is 6, which is 1.216. Okay. Now, Sq is equal to 1 plus tan phi B by L, which is 1 plus tan 20 degree into 3 divided by 6, which is 1.182. Similarly, S gamma is equal to 1 minus 0.4 into B divided by L, that should be equal to 0.6. So, it is coming 1 minus 0.4 into 3 divided by 6 into 0.8. So, which is greater than 0.6. So, we have to consider the 0.8. Now, similarly, DC we can get 1 plus 0.4 K. Now, for df by B get less than equal to 1, my K value is df by B, and our case this is df is 1 and this is 3, which is less than 1. So, this will be df by B. So, this will be 1 plus 0.4 into 1 divided by 3. So, this will be 1.133. Okay. So, now the similarly I can calculate the dq, which is 1 plus 2 tan phi 1 minus sin phi square into k. So, k is also df by b here. So, that will be 1 plus 2 tan phi 1 minus sin phi square into df by b. So, finally, I can put 1 plus 2 tan 20 degree 1 minus sin 20 degree square into df 1 divided by 3. So, this is 1.105. Okay. And we know that d gamma is equal to 1 for all the cases. So, finally, q ultimate is, or net ultimate will be 50 into 14.8 into 1.216, because that is the SC 1.1, then DC is into 1.133, then inclination factor is 1, because all IC, IQ, I gamma will be 1. So, 1, but the compressibility factor CC is 0.914, and then plus 18 into 1, then the 6.4 into 1.182, 1.182 SQ into dq is 1.105, and that is 0.94 the compressibility factor, then the inclination factor is 1, then plus half, unit weight is 18, B value is 3, bearing capacity factor is 5.4, then all the factors. This is DC is SC is SQ is 0.8, sorry, S gamma is 0.8, then D gamma is 1, then inclination factor is 1, then the compressibility factor is 0.94. Okay. So, the value, and then it is net ultimate. So, that will be minus gamma is 18 and df is 1. So, this value is 1164.92. Okay. So, this way we can incorporate the compressibility effect of the foundation. So, if you neglect the compressibility effect, as you can see the compressibility factors are close to 1. So, this value will be more or less same there, or the values will be slightly higher if I do not consider the compressibility effect. But in this case this value is close to 1, but maybe if the elastic modulus or the rigidity of the soil is less, then I will get a significant amount of reduction of the bearing capacity value if I consider the compressibility effect. So, that depends on the type of soil, the properties of the soil. But again, when you calculate the these factors for eccentric loading, remember that, then in other theories this recommendation not such given. So, for my opinion, you consider B dash L dash in place of B and L. Okay. So, in the next class because I have discussed the different effect that I will discuss in this course. So, first one I have discussed the effect of soil compressibility. So, next class I will discuss the other effects like the loading eccentricity and then the inclination of the load and the other effects. Thank you.